Things are going okay? Yeah. All right. Well, we talked last time about complex numbers, and we're going to use complex numbers to help us find zeros as we go through. But we just want to make sure we know how to do different operations. So we talked about reminding ourselves how to add, how to subtract, how to multiply. We didn't do divide quite yet, so let's do that real quick. You probably already talked about this, which is why I'm going a little bit faster. Anyway, when we do the complex conjugate of a number, the idea behind this is to help us get the I out of the denominator. My goodness. So what we use for what we refer to as the complex conjugate is you flip the sign in the middle. And the reason why you flip the sign in the middle is that if you, let's just, I'll do it with letters and we'll do it with numbers here in a second. If I multiply a complex number by its complex conjugate, notice that you'll get a squared in the front, right? What happens when you multiply your outer and your inner together? What happens with those terms? So you get ABI, a positive, and you get a negative. So what's going to happen with those? Those are going to cancel out, right? And so at the end, we'll get a minus b squared I squared. But what did we say I squared was equal to? Negative 1. Bless you. So that turns into a squared plus b squared. No i's in it, right? That's what multiplying by the complex conjugate allows you to do, is it gets rid of the I. Okay? So that's how we do complex number division. We multiply here top and bottom by the conjugate. And it's going to do the same thing on the bottom every time. We'll multiply it out here in a second, but the next one we'll just see what we'll just talk about what we get when we multiply. If we distribute the 2i through the top, you get 12i minus 4i squared, right? And if you multiply out the bottom, you get 36 minus 12i plus 12i minus 4i squared. I just multiplied it out, all the distributions, right? Like you would if you're doing FOIL or just distributing the 2i through. Right? How can we rewrite 4i squared? Minus 4i squared, I guess I should say. A positive 4, right? Because again, I squared is negative 1, so it just flips the sign. On bottom, what goes away? Yep, those go away. And we get 36, and then on the end we get plus 4, right? Notice where notice the 36 and the 4 here. The 36 is that thing squared, isn't it? And the 4 here is that thing squared, isn't it? Okay. So without having to write, you wouldn't have to write this out every single time. It's going to work that way every time when you multiply by the conjugate. It's the first number squared plus the second number squared without the I in it. Okay. Now we simplify. Typically we write the real part first and then the denominator, then the complex, the imaginary part. So we'd have 4 plus 12i over 40. And again, if you want to put this into standard form for a complex number, I would want to write it as real part plus imaginary part. So I can split my fraction up as 4 over 40 plus 12i over 40. And then you can reduce your fractions a little bit. You get 1/10 plus 3/10 I.
Why did we eliminate the i's? The I squared.
I squared is equal to -1.
Okay.
So we're replacing I squared with negative. That's why it's flipping the sign. Yep. Okay. All right. So what would we do in the next one if we're trying to simplify this? Well, if we want to simplify this and do the division, so we multiply by, yep, the 3 plus the 9i over 3 plus the 9i, right? We're going to flip the sign in the middle. Now we'll distribute out the bottom, distribute out the top here in a second. But what I just told you a minute ago, what should you be getting in the denominator? 9 minus 81i squared, right? I can write today. I was having trouble in my last class too. Right? Remember, it squares this part and squares that part. What do you get when you distribute out the numerator?
Minus 45 plus 18 plus 54 I squared.
And we're doing our distribution just like what you would do with any polynomials, right? It's just FOIL, nothing big there, right? The denominator, the same idea. We just have the middle terms are going to cancel. They're going to go away. So what does the top simplify to now?
15 minus.
They're opposite signs. You added them together.
27.
Yeah, it should be minus 27i.
Plus. No, minus 54.
Minus 54. Good. And the bottom will be
9 plus 81, so 80. No, 90.
90. Good. Negative 15 minus 54 is negative 69. Then a minus a 27i over 90. And then again, we should split it into two pieces. And then it looks like a 3 will go into top and bottom. And a 9 will go into top and bottom in the second part. Is this okay? The concept okay? Okay. Now, the important part here is the idea of this conjugate and basically getting rid of the i's when you multiply it together. All right? All right. So we'll come back to that here in a second, but let's talk about the whole point of what, by the way, I guess brain scattered. Sorry, let me try again. One of the reasons why we're talking about complex numbers is because when you look for zeros of polynomials, sometimes those zeros turn out to be complex. You've done that with the quadratic formula before, right? Remember, quadratic formula has that square root of b squared minus 4ac part, right? So if you get a negative under the square root, you're going to get a complex number, right? So one of the reasons why we're reviewing complex number ideas is to help us find the complex zeros of polynomials, okay? Our goal here overall is to find all possible zeros that we can, okay? So if we have a polynomial that we don't see how it factors right away, we might want to find some candidates for what we think might be zeros. And one of those ideas is what's referred to as the rational zeros theorem. Okay? So in the rational zeros theorem, the important pieces are the leading term, in particular the leading coefficient, and the constant term. Okay? So if you have a rational zero, remember rational number, the root word of rational is ratio. So a rational number means a fraction, okay? Some integer over another integer, okay? That every rational zero of f of x has the following form. We usually write it as p over q, where p is a factor of the constant term, that a naught, and q is a factor of the leading coefficient, the an. Okay. What this process does with finding possible rational zeros is gives us a list of things to try. Okay. So let's look at this first example. It asks us to list all the possible rational zeros of 8x to the 6th minus 12x to the 4th plus 13x squared minus 4x plus 25. That's a lot of words. Okay. All right. But again, the only things that matter are the constant and the leading coefficient. What is the constant in this case? 25. Good. So first thing we want to write down is factors of 25. What are the factors of 25? Okay, so 1 works, and 5 works, and then 25, right? That's it. So we have. What's the leading coefficient? 8, right? So the leading term is 8x to the 6th. The leading coefficient is 8. So we want factors of 8. What are your factors of 8? And a 2, right? 1, 2, 4, 8, right? Right? Okay. All right, so now when we make our possible rational zeros, we're going to be very, very systematic about this, okay? These are our possible, again, going through this, notice what the rational zeros theorem says. The numerator has to be a factor of the constant, right? So these are your possible numerators here. Oops. I can spell I tell you what, my spelling today is atrocious. If you get an email from me today, I look for multiple typos because I cannot spell today. All right. Possible numerators. Those are your possible tops, okay? Rational zeros theorem says that one has to be a factor of your leading coefficient, right? So these are your possible denominators. Okay. All right, so when you do your possible rational zeros then, I want to do all possible combinations of one of these over one of these. So let's think about how many we're going to get, and we may get repeats, but how many are we going to get? I've got 3 for every 3 I compare any of these 4, so we're going to end up with 12 of them, right? So we'll just write them out longhand here. I usually like to do all my numerators over one denominator, then do it over the next denominator and go across. That's how I do it systematically. So we can have 1 over 1, 5 over 1, ooh, hey, 25 over 1. That's your first set. The next one would be 1 over 2, 5 over 2, 25 over 2. And then 1 over 4, 5 over 4, 25 over 4. And finally, 1 over 8, 5 over 8, 25 over 8. Okay? That's a long list. Well, it's going to get twice as long. Okay? Notice it says it just has to be a factor of it, right? That doesn't say whether or not that factor is positive or negative. For example, 2 times 4 is 8, but also negative 2 times negative 4 is 8, right? So I can do all pluses or I can do all minuses. So I'm not writing it down twice. A shorthand way to write this would be put braces around the whole thing and put a plus or minus out in front. It could be positive any of those things or negative any of those things. Okay. Now you could have reduced your fractions in a couple of places. 1 over 1 is just a 1. 5 over 1 is just a 5. 25 over 1 is just a 25. Okay. All right. Is okay? All right. So again, these are just the where they could possibly cross if it's going to cross at a fraction. It doesn't say that it's certainly not going to cross at all of them, and it may not cross at any of them. It's just giving us a potential list. Okay? So work on the next one for a second. See if you can figure out the possible rational zeros, and then we'll go into how we actually use this information to help us out later. Ready to chat? Still writing? Now, again, if you have repeats, you don't have to write the repeats if something reduces as a repeat. Because otherwise, you're going to be writing how many? 64 fractions? It's a lot of fractions. Did everybody get the list of factors? Do you agree with my list of factors that are up on the board? Yeah? Yeah? Okay, cool. All right. Let's start seeing if we can find some fractions here. I did the first 8. That was pretty straightforward, right? Because that's all of the factors of 42 over 1, right? I just didn't write it over 1. We okay with those first 8? What would the next, if I go to my next denominator, what would be the first fraction? 1 over 2, and then I did everything over 1. What's the next one going to be if I do everything over 2? Maybe a 1. I've already written 1, right? Because it would be 2 over 2, so I don't need to rewrite it. What's the next one? 3 over 2. The next one would be, it'd be 3, wouldn't it? 6 over 2, but we've already written 3. We don't need to write it again. We would have 7 over 2. 14 over 2 is 7, which we've already written. We'd have 21 over 2. And then 42 over 2 is 21, which you've already written. So I only didn't need to write all of them again. Yes? No. You can write them all. It's just you don't have to write them all, is what I'm saying. Yeah. Okay. What about the next group? What would be the first one? We've done all the denominators with 2. Now with 3, what would you get? Other way around, right? 1 over 3, 2 over 3, but then we'd have 3 over 3, which is 1, which we already have. 6 over 3 is 2, which we already have. 7 over 3, 14 over 3, 21 over 3 is 7, which we already have, and 42 over 3 is 14, which we already have. And then do the same thing for fourths. I'd have 1 over 4, 2 over 4 is a half, which we already have. 3 over 4. 6 over 4 is 3 halves, which we already have. 7 over 4. 14 over 4 is 7 halves, we already have. 21 over 4. And 42 over 4 is what? I just lost it. 21 halves, which we already have. And then do the 6s, and then do the 8s, and the 12s, and the 24s. Is the process okay, what we're doing? It's very, very tedious. You're not going to have to do this many on the test, I promise. Okay. So the next one's going to be 1 over 6, 2 over 6 we already have, 3 over 6 we already have, 6 over 6 we already have, 7 over 6, 14 over 6 we have, 21 over 6 we have, 42 over 6 we have. Basically, you already have it in the list if you have common factors that factor out. Okay. The next one's over 8, 1 over 8, 2, 3 over 8, 6 over 8, 7 over 8, 14, 21 over 8, and 42. And basically, I don't need to write anything that's got common factors because they've already been reduced at some other stage. Okay. For what am I at? 12ths. 1 over 12, 2, 3, 6, 7 over 12, 14, 21, 42. That's all I have because all the rest of them had common factors. And then the last one is 24s. 1, 2, 3, 6, 7, and that should be it. The rest of them should all have all be repeats. All right, that's a lot. Okay, but again, is the process okay? Tedious, yes. Totally 100% agree. But notice I was very systematic, right? Did all the numerators over the first denominator, all the numerators over the second one, and just kept going. Okay. All right. So we're going to do this process to help us find all of the zeros. of functions. Okay, so this is what we're going to be basically doing the rest of this section and the next section. Yes.
How are we supposed to tell which one of these numbers the factors of are the numerator or the denominator? Because in the first question,
It's always the factors of the constant or the numerator. The factors of the leading coefficient or the denominator. Yep. Okay. All right. So finding zeros, typically we try to factor, right? Does this look like it's something easy to factor? No. This looks hard to factor, right? Because again, we've got 4 terms in our polynomial. Your main technique for trying to factor a 4-term polynomial would be grouping, right? But notice here, if I factor out an x squared out of that, and then factor a 2 out of that, I'm not going to end up with the same thing to factor out, right? So this is where we're going to use the possible rational zeros here. So let's get that list first, okay? What are we going to look for factors of to help us find the rational zeros? Factors of 8 and factors of 3. What are your factors of 8?
1, 2, 4, 8.
And your factors of 3? That's a little smaller list, isn't it? So what are your possible rational zeros then?
1 over 1, 2 over 1, 4 over 1, 8 over 1, 1 over 3, 2 over 3, 4 over 3.
Okay. And it's plus or minus all of those, right? So take all of them over 1 to start with. Oops. Put all of them over 1 to start with, and then all of them over 3. That okay? Now the question is, which one or ones is it? Right? That's 16 total. That looks like a lot to check, doesn't it? Okay, so we're not going to do that. Here's what we're going to do. We're going to go over to a graphing utility, and we're going to graph the function that we just found. So it was whatever the function is, 3x cubed. Of course, I lost my numbers. Negative 11, negative 6, and plus 8. Minus 11x squared. Minus 6x plus 8, right? Yep. Okay. And I need to zoom this back out because this is from the other day when I was showing you things. There we go. Okay. All right. So here's a graph. I don't really care what the numbers are. I'm just looking for things that look like they are rational, look like they're fractions, look like there's something in my list. Do you see a number in there that looks like one in your list? What do you see? Well, 1 would be about right here, so 1 doesn't work, but the negative 1 works, doesn't it? Yeah, and what else? Positive 4, yeah. Okay, so let's try 1. See if which one, it doesn't matter which one we try, let's try 1. We suspect that we've got a negative 2. This is probably about 2/3, it looks like. But this one's at 4, isn't it? Okay, so let's just try 1. Which one do you want to try? The negative 1. Okay. Remember how we try it? We use synthetic division, right? If we plug the number in and get 0 out, that means it's a 0. Okay. So we'll do this with synthetic division. I'll use negative 1, 3, negative 11, negative 6, 8. How do we do synthetic division again? Yeah. So yeah. Multiply then add, right? Bring down your 3, multiply, we get negative 3, add, we get negative 14, multiply. Positive 14, right? What happens when we add now? 8, multiply. Negative 8, add, we get 0. So did that work? Is that a 0? Okay. So far, what do we have? We've got 3x cubed minus 11x squared minus 6x plus 8. Well, since we plugged in negative 1, what was a factor? X plus 1, right? Because it flips the sign. What's the quotient? That was the quotient, right? Okay. Remember that it drops the power by 1. We started with x cubed, so we're now at x squared, and these are your coefficients. Okay. Once you get to a quadratic, you're essentially done, because either you'll be able to factor it, but if you don't see how to factor it, what can you always do? What formula can you always use for a quadratic? What formula can you use for a quadratic? Quadratic formula, right? Your goal in these problems is to get down to a quadratic so that you can either factor or use quadratic formula every single time. Okay? This does factor, but just a remind about quadratic formula, if you've got 3x squared minus 14x plus 8 equals 0, what does x equal again? Negative b plus or minus square root of b squared. Yeah. B squared minus 4 times a times c all over 2 times a, right? If you don't know that, you're going to need to know that for the test on Friday. Okay. 14 plus or minus, let's see. For 12 times 8 is 96, so we just get 100 under there. All over 6. Square root of 100 is 10. Now remember what the plus or minus means. You do 14 plus 10 over 6, or you do 14 minus 10 over 6, right? So you get x is 14 plus 10 over 6, 14 minus 10 over 6. 14 plus 10 is 24, divided by 6 gives you 4. 14 minus 10 is 4 over 6 gives you 2/3. Right? And isn't that what we saw on the graph, by the way? The other two roots were 4 and 2/3. Yep. Okay. So when we factor this now, we have to be a little bit careful. Since 4 is a 0, what has to be a factor? If 4 is a 0, what has to be a factor? X minus 4, right? We agree? Since 2/3 is a 0, what has to be a factor? X minus 2/3. But notice, if I do that, is your leading coefficient going to match up? If I write it that way, does your leading coefficient match up to what you started? The leading coefficient on the left is what? What's the leading coefficient that we have currently on the right? What we have currently. So an x times an x times x is the 1x, right? How do you think we're going to make them the same? What do you think I need to put out in front? A 3, yeah. Just match it up. Okay, that'll do it. What questions do you have? Yes. Is a 5-part question? Sure. I don't know. I didn't count number of parts. It's a long problem.
So you do factors and then you pick whatever 0.
Yep.
Then you do the quadratic.
Yep.
And that's it.
And that's it.
Okay.
Yeah.
Cool.
Yeah. No, we'll get more. We may have to do it twice because we may get higher degree powers, but yeah. But this is the process. All right. Let's skip the next one. I'll leave that for practice. Let's do this one. Let's do number 5. Okay. First thing we're going to do is find our possible rational zeros. What 2 numbers are we going to look at?
1.
Yep, 72 and 1, right? So factors of 72 and factors of 1. Well, what are the factors of 1? 1. Whew, that was hard. How about 72? 1 works, 2 works, 3 works, 4 works, 6 works, 8. The easiest way to do that is just start dividing. 72 divided by 1, 72 divided by 2. Just work all the way through up to it. Eventually, you'll get to, when you divide it by 8, you get 9, and then they start to pair, right? And you get 12, 18, 24, 36, 72. That's what a calculator is for, right? Eventually they're gonna pair up, right? I just started with 1. 1 divides it, 2 divides it, 3 divides it, 4 divides it, 5 doesn't, 6 does, 7 doesn't, 8 does, 8 paired with 9. And then I just write out the other pairs. You only have to get roughly halfway there. Yep. Okay. What are your possible rational zeros then? This is, yeah. It's just the same list, isn't it? Good. 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, 72. That's a lot of numbers. Phew. I would not want to check all of those, right? It looks like there's 12 times 2 because you have to do the plus or the minus. Back before graphing calculators were around, you basically had to guess which ones they were. Okay. That sucked. Trust me. It sucked when I was in high school to do that. Okay. All right. All right. So let's think about what we do instead. We get a graph. Now, do not go out and buy a graphing calculator. Okay. I will put a graph on the exam for you so you'll see it. So do not go out and buy a graphing calculator. When you're doing your homework or practicing, use Desmos or something like it. Okay. But I will put a graph on the exam for you. You do not have to do it yourself. Okay? Deal? Deal. All right, cool. All right. Now you're going to have to remind me what the heck the polynomial is so I don't have to go back. Hold on a second. I got my keyboard attached here. X to the 4th.
Minus 2x to the 3rd plus x squared. Minus 18x minus 72.
Thank you. All right, looking at that, where does it look like it crosses the x-axis? -2 and 4, right? Okay. So let's shoot back over. Let's try them. Which one do you want to try first? 4? And we'll do this with synthetic division again. 1, -2, 1, -18, -72. Goodness gracious. What do we do first? Drop the 1. Then we multiply, and then we add, and then we multiply, and then we add it, multiply it. What's that? You're okay. We bring the 1 down, and then multiply by the number in the corner. And then 18. 18 times 4 is 72. You get 0 when we're done. Now again, we want to see 0, right? If it is a 0, which we saw on the picture, then we want to see 0 when we're done. If you don't see 0, but you think it's a 0, then you've probably made an arithmetic error somewhere. Okay? All right. What was the degree we started with? 4. So what is it as an answer? What is this? What would be the degree here? 3. What did I tell you I wanted you to get down to, though? Quadratic, right? That's our goal, right? We've knocked it down by 1 degree. How do you think we can knock it down by another one? Do the other one. Fantastic. We have another root that we see, didn't we? So use the other one. Wonderful. I like that attitude. Do the other one. I could write it again, but I'm just going to make a tower. Right? These are the coefficients we want, right? I don't need this one anymore because that's the 0. That's the remainder. I don't need it. I just need to use these. Process again is to do what? Drop down the 1 and then multiply gives you -2. Add, we get 0. Multiply 0. Add 9. Multiply -18, right? And then add, we get
0.
0, which is what we're supposed to get, isn't it?
Okay, now I'm.
Did we get down to a quadratic now? Yeah. As a matter of fact, our original function is x to the fourth minus 2x cubed plus x squared minus 18x minus 72. What's one factor? Yeah, so the factor will be
Okay, x4.
x minus 4, right? Another factor is x plus 2, and the rest of it's going to be what? Looking at this part here, what's the rest of it going to be? X squared plus 9, right? We agree? Because that was our quotient at the end, isn't it? Yeah? Okay. So now we need to find, this is the quadratic we need to find the zeros of. We can do this a couple of different ways. It doesn't factor, right? It'd have to be x squared minus 9 to factor, right? Okay. So you can use the quadratic formula again, or why don't I just subtract the 9 and then take the square root. Remember, when you do square root of both sides, you get plus or minus. What do we do with the negative? Makes it an I, and square root of 9 is 3, so we get plus or minus 3i. Okay. So your zeros are 4, negative 2, 3i, and negative 3i. Do you think you can figure out the factorization now at the bottom here? What can we replace x squared plus 9 with? Using the same principle like we did here. 4 was a 0, x minus 4 is a factor. Negative 2 is a 0, x plus 2 is a factor. 3i is a 0. What's a factor? X minus 3i. Negative 3i is a factor. X plus 3i. Good. Exactly right. Yeah.
So why did we synthetically divide using our answer instead of just with the original again?
Because if I would have done with the original again, I would have still done it in x cubed.
Oh.
Right? I'm trying to knock down the degree every single time. Okay.
So you can just do that with any.
Yep, we're gonna do it with
Just
any of them.
continue.
Yep, we can
Okay.
just continue it up top. So it'd be like if I wanted to try to completely factor say 108. I know that 2 divides into it and I get 54. I could also then divide a 3 into it to give me a 9. Or not a 9, an 18.
So you can just.
I can just keep scaffolding it down. Yep. Let's do one more real quick. Make sure we're all on the same page. I'm going to skip the next one. Yes. Oh, you want me to go back up? Yeah.
Why is there only for the negative 2? Explain what.
Mm-hmm. Why? Which one?
For the negative 2. Why did you do it for 1, 2?
Off of here?
1, 18, and 85?
Okay, so we divided. We divided our original polynomial by x minus 4 and got this answer, right? I'm also going to divide it by x plus 2. So I'm going to work off of the answer and divide it again. Why the negative 2?
Yeah.
Oh, I went back to the graph. That part right there.
Oh, okay. So you showed the point.
Yeah, I chose another point. Yep, another point. Yep. Okay. Yep, you're welcome. Let's do one more here. Let's see here. There we go. Let's do this one. This is number 11. I'll put solutions up to the other ones too so you can see them. That'd be okay?
Yes.
Yeah? That'd be a good idea?
Yes.
Okay, cool. Let's look at 11. What do we look at factors of? For 30 and 2. What are your factors of 2? That one's easy. 1 and 2. Factors of 30 are, let's see, 1 goes into it 30 times, and 2 goes into it 15 times, and 3 goes into it 10 times. 4 doesn't. 5 does. 6 times. And there's where they pair, right? And we're done. So writing out your possible rational roots. What are they? All of the one. Oh yeah, all of them over 1.
1 over 2. 1 again. 3 over 2.
Yep.
3 again.
10 over 2 is 5, and 15 over 2, and then 15 again. So that's it. After that, what's our next step? Graph it, right? Once we get our possible rational roots, we're trying to see which ones in the list might work, right? So if I flip over to the graph and go back in 2, 1, negative 16, negative 3, 30. 2, 1, oops, negative 16, is that right?
Yep.
X squared, 3? Minus 3x, and then plus 30? There we go. Okay. All right, so zooming in a little bit, what looks like it might work? Well, 2 might work. Right. This one over here is negative 2.5. Yep. That's negative 5 halves. So try those 2, right? Okay. So let's see what happens here real quick on one of these at least. Oops. What do we say? 2? Okay. 2, 1, negative 16, negative 3, positive 30. Bring down the 2, multiply, get 4, 5, times 2 is 10, negative 6, times 2 is negative 12, negative 15 times 2 is negative 30, and we get 0. Is that a good thing?
Yes.
That's a good thing, isn't it? We agree?
Yes.
Okay. What was the other one we saw?
5 halves.
Negative 5 halves.
Yes.
I know it's quick. We got about 1 minute here. 2 times, bring down the 2, multiply, we get
Negative 5.
negative 5. Add, now we get 0, don't we? Multiply, we get 0. Add, we get negative 6.
You get 15.
Yep, we get a 15, and we get 0. So that one worked, right? Okay. So far we have x minus 2, x plus 5 halves times what else? 2x squared minus 6. And so then that would be the one that we would need to solve next. Remember again, your goal on these is to get them to a quadratic, right? Okay. I will get solutions posted on Moodle to the rest of these so that you have them. And if I have time, I might even talk through a couple of them and record them as videos. Would that help?
Yes.
Okay. All right. That'll probably be by tomorrow and not today. I just got 2 meetings added to my schedule for today. So it probably won't be today. So, but I will get some by tomorrow. Have a good one, everybody.